Hello everyone, my name is Jie Lian, a PhD student from University of Louisiana at Lafayette. Today, I will present our work, EcoSpot, spotting your locations via acoustic sensing. Nowadays, indoor localization supports many applications in smart homes. Good examples are security surveillance, elderly care, crowd monitoring, and fitness tracking. A person may spend almost 88.9% of the day indoors. The market value of indoor positioning and indoor navigation is expected to exceed $23.6 billion in 2023. This shows indoor localization have large market value. As such, there is a large demand for effective indoor localization technology. Recently, we have seen a lot of different approaches for indoor localization, such as IMU sensor, camera, flow sensor, light sensor, Wi-Fi, radar. Compared with these approaches, the acoustic-based localization is more appealing. The acoustic-based localization relies on the ultrasound or human talking to localization. The advantages are, compared to camera, it will not be affected by the lighting condition. Compared to Wi-Fi, it will not occupy the communication bandwidth, and the low frequency of the acoustic signal enable it to be processed by the home device. However, existing acoustic localization systems mainly rely on the microphone array to process the signal. The layout of the different microphone array would affect the performance of such system. Another problem is, not all home devices have microphone array. Restrict the deployment of this system. To tackle with such problem, we propose EcoSpot, an ultrasonic-based localization system that does not rely on specific hardware. We designed the EcoSpot to meet the following goals. It could provide no intrusive user experience, means it does not need users perform any specific actions such as talking. It does not depend on specific hardware. We expected EcoSpot could be deployed to any hardware. The key idea of the EcoSpot is that we localize the people by the help of the wall reflection. The wall can be seen as a virtual signal sender so that we can localize a person with just one speaker and one microphone. The figure shows the location model. R represents the person and S represents the EcoSpot. The EcoSpot consists of a co-located speaker and a microphone. The S would emitting the ultrasonic signal and R would reflect the signal. In this figure, XY represents the relative distance of the person to the microphone. The position of the EcoSpot is assumed to be known. Then we could model the position of XY as a function of the body reflection and wall reflection. Here is the system overview of EcoSpot. The EcoSpot composed of 4 components: signal generation, TOF profile generation, localization, and location correction. In signal generation model, we generate a carefully designed FMCW signal to sensing the environment. In TOF profile generation model, we apply the cross correlation between the transmitted and received signal, and we eliminate the interference of the static object to get a clean TOF profile. To determine the body reflection, we picking up the strongest peak from the clean TOF profile. The strongest peak corresponds to the body reflection. We could calculate the body reflection by the corresponding lag value. To determine the wall reflection, we consider the human body as the virtual sender and the reflected signal from human body to the wall as the virtual sending signal from the virtual sender. We only take signals at the time interval between the longest and shortest reflection as our virtual signals. Due to the similarity between the wall reflection and body reflection, we could apply the cross correlation to identify the wall reflection signal. As figure shows, 2 sets of strong peaks appear on such TOF profile. The first peak cluster can be considered as the direct transmission from the virtual sender, and the second cluster can be considered as the nearby wall reflection. By corresponding the lag value of the second cluster, we could get value of the wall reflection. By combining the wall reflection and body reflection, we could get the location of a person. Finally, we apply a Kalman filter to correct the location. Here is the experiment of EcoSpot. The left figure shows the EcoSpot performance of tracking the moving person. The red line indicates the ground truth trajectory. The irregular blue curve represents the measured trajectory by our EcoSpot. The average trajectory error is 21.9 centimeter. The red figure shows the EcoSpot performance of locating a static person at different reference points. The red points indicate the reference points. The blue points represent the spotted location by our EcoSpot. The median localization error is 12.4 centimeter. The results demonstrate EcoSpot can work effectively both to locate the static person and to track the moving person. Here is the conclusion. We implement EcoSpot, leverages only one speaker and one microphone to localize via acoustic sensing. We conduct experiment to validate the feasibility of the acoustic sensing in the room scale environment. Thank you for listening.